start button, it starts the program. The camera will be recognizing the dice on the conveyor belt and feeding that information to the robot, which will then pick them up and sort them in order of 1 through 6 on these trays. If it grabs an extra dice that it doesn't need at that moment, it will put it in the buffer,
which it can grab from later on.
So that's our factory downstairs in the Crabtree building. Just a short introduction to what we want to accomplish with this project. Our goal was to improve the production in our dice factory that you saw. We've been collecting data for a long time now, and we've been hoping to improve the quality of our production as well as the performance of our factory. The problems we've been facing, like most factories, we want to have a lean process where we don't have a lot of raw materials. But this is only possible if we really understand where bottlenecks occur in the process and where we can cut costs without hurting our production. So in order to achieve these goals, we're focusing on 4 specific outcomes. The first one is robot utilization, which is how much our robot is working to sort the dice versus how much it's waiting for dice to come. We're also going to be looking at the number of defects, which is how many defects our factory sees, and that's the dice being produced. We also have how many of those dice are being produced in a certain span of time, as well as how many trays that those dice are packaged into are defective, or how many of them don't have the right number of dice.
For our source of data, we created the data on our own, like Andrew was saying. So we've run the robot and we have logged the data over time, and the data that we are using in this project is just a snapshot of the data that we logged from a day and a half. So we have 130 records of 5-minute intervals, 12 input variables.
These are the variables we're using. So those are the first 4 of the outcome variables that we already explained, and all of those are numeric outcomes. Robot utilization is the only one that's continuous. All the other ones are discrete numbers. We also have inputs like timestamp, which is when when that record was logged, and that one we had to manipulate to give us useful information. And so instead of giving us the time, it actually just gives us, it starts at 1 when we start production, and then it increments by 1 for every record. We also have the robot speed, how fast the robot's moving, and missed dice defects is how many dice were missed in a 5-minute interval.
We also have conveyor speed, which is how fast the conveyor belt's moving. Buffer size, how many dice are in the buffer at the start. Number of trays is how many trays are produced. Force fill defects is when the robot will fill a tray with a wrong number dice out of necessity. Downtime is a percent of time that the robot is stopped. Number of air blasts is sometimes the dice are jammed in the system and it will blast it with air to break it up, and so that's how many times it occurs. Failsafe forces is when the robot is waiting for too long, it will just do a force fill.
So for our first results, we have robot utilization. We found that CART was the best algorithm in predicting how much our robot was being utilized. It gave us a good R-squared, but also we were really happy about, we're focusing on the RMSE because we're well within 10% of our predictions on when you square those errors. And so it's between 0 and 100%, so we were excited about that. CART was the simplest of all of them. That's also why we used it. So we excluded buffer size, number of defects, number of batches, and force fill defects because those were all collinear. In addition to those, we also ended up excluding downtime, dice produced, and missed dice defects because they weren't significant when we ran MLR, and when we removed it, it didn't change our CART predictions. And then when we looked at our CART predictions, we found that the first 2 splitters were failsafe, force, and timestamp. So those were the most significant. these are the results for the number of defects. So again, we tested a lot of different models and we found that boosted tree was the best algorithm for detecting how many defects there would be. We didn't use missed dice defects, force fill defects, or defective trays because those are used to calculate the total number of defects. We also excluded buffer size and number of batches because of collinearity. And then we found after we ran the model that downtime was insignificant. We removed that variable from our predictions and found that our results were unchanged. Looking at our cart, you can see that the first two splitters were air blast and dice produced. Those were the two most significant variables.
We got pretty good results when trying to predict dice produced. As you can see, we found ANN with the most significant variables to be our best predictor with a 0.85 R squared and a 14.1 RMSE. We used MLR to determine which variables were most significant in predicting dice produced. We found that downtime and failsafe forces were the strongest. Everything with a p-value below 0.05 we removed and got slightly better results in predicting dice produced. For defective trays, we found the best algorithm to be KNN with the most significant variables. We got an R squared of 0.62 and an RMSE of 1.1. We always excluded num defects, force fill defects, and missed dice defects because of high correlation. In predicting defective trays, we found that the strongest predictors were num air blasts and num trays. And we found this using CART. We decided not to use MLR because it did not perform well in predicting defective trays.
So as you can see, we were able to get pretty good results for our 4 outcome variables. Even though in some of the cases R squared isn't very high, we were happy with these results because the RSME was still really good, a lot better than what we had been getting previously.